Inside thermal power plants, we always hear that a flushing must be done in a lubrication system, or that there are specific conditions necessary to do so. But what exactly is a flushing? Is there a standard definition when it should be executed? What are the types, standards, and technical details for performing efficient flushing? That's what I'm going to talk about in today's video. So stay with me until the end, which is quite complete. And I warn you that it will be quite extensive. Consider mirroring to your TV for smoother viewing, or be guided by the themes highlighted here in the timeline below. Optimal reliability of the turbine system is that it is a well-designed lubrication system, and the use of a good lubricant that is free of contaminants. Achieving this requires the use of appropriate purification methods to ensure the oil is free from harmful contaminants. Your turbo oil purification solutions limit machines acceptable and correction of non-compliant MPC related to varnish contamination, in addition to removing water from oil using technology up to 30 times more efficient, faster than a traditional vacuum thermo. I've already talked about it in other videos here, and I'll leave it in the description, so you can check it out after this video here. TURBIVAP has concrete solutions for your lubrication system, be it services, equipment, or solubilizers for the oil system. Therefore, please contact us if you need support in these matters. In addition to the efficient purification system, a continuous monitoring program is also necessary to ensure oil quality is within specifications, and that corrective actions are taken to minimize the formation and entry of contaminants into the system. The benefits of purifying and operating lubrication system can be significantly reduced, but it's no use if they are not initially cleaned to the level which will prevent damage to components on initial startup. After manufacturing or maintenance, thorough care and cleaning are necessary to minimize and remove contaminants during manufacturing, intervention, installation, or a combination of all these moments. How will contaminants remain from these processes? It is necessary to wash or flux and purify the system to remove them before the turbine starts. Continuous purification is necessary to keep the oil pure during operation unless there is a catastrophic failure. The most common time when turbine maintainers perform flushing between oil changes. But, as we will see, it is not or should not be only at this moment. On the other hand, a flushing would be necessary every time we change the turbine oil. There is no practice or standard to determine this. However, removing degraded oil and deposits from the interior of your lubrication system certainly seems to make sense. Before charging your system with new oil and filling the dirty lubrication system with new oil can have an significant impact on the life and performance of this new oil. Therefore, the safety of performing a flushing in certain moments that we will see ahead make perfect sense. Reliability increases and risks are reduced, such as in scheduled shutdowns and new systems. The emphasis of a flushing is in the removal of contaminants introduced during manufacturing, storage, field adjustments, final installation, and operating systems. The emphasis is on removing contaminants that are generated or transported during operation and for malfunctions that occur during operation, or contaminants that are introduced during overhaul, or even both. Before continuing, if you like this video, leave a like or dislike, leave a comment on what you think, and subscribe to the channel if you are not already subscribed to receive notifications of new content like this. Also remembering that this is the summarized version on this subject. The complete, detailed, and extensive version, as well as other topics about turbines, you can find it in our steam turbine course. I'll leave the link here on the card in the description of this video. Consider knowing and taking it to your company. We have several formats. Visit our website. Also discover other solutions for turbo machines. After all, what is a flushing? According to ASTM D6439, the standard guide for cleaning, system flushing and purification, for lubricating steam turbines, gas turbines, and turbines. For hydroelectric power plants, flushing is defined as circulation of liquid through a lubrication system or component when the turbine is not operating to remove contaminants. While this may constitute the standardized definition of a turbine flush, in practice, a flushing can mean many different things. Typically, they are categorized as cleaning, mechanical, chemical, or enhanced solubility system. So to begin to understand more regarding flushing, it is worth noting that the term flushing is generic. Therefore, to address this issue between machines, we need to know and specify what type of flushing we are referring to. To do this, we need to highlight some specific types of details, and I will highlight just a few. To begin with, the best known flushing is perhaps the discharge flush, or oil change, generally aimed at new systems and systems with service hours, and typically does not require active surface cleaning or a wipe down. Improved, provided for example, by high-speed flushing. In this case, a system discharge circulation is performed with the sacrificial oil, also called base oil, which has similar properties to oil and is used definitively in the equipment, mainly the issue of viscosity, or it could also be the operating oil itself. The process must be carried out hot, using the equipment's own pumping system, and this type of flushing is described in detail in this standard that I mentioned. Very similar with this discharge flushing, but with some particularities. We also have the so-called circulatory flange, usually done on commissioning, and a flushing guided by O&M. Therefore, it is not standardized. In this case, the achievement of the minimum number of measured displacements is not guaranteed. At Reynolds, therefore, it does not cause induced swirling in the oil. Don't worry, I'll explain this in more detail. In this case, therefore, it is obviously not necessary either. The use of auxiliary external equipment such as pumps and other devices. The turbine's own system is used. In that case, as expected from the subsystems, they should be satisfactorily clean. Low oil swirl speed may be sufficient to achieve the OEM's desired NOS parameters. But these are not the only types of flushing. In fact, as I said, in this last case, the circulatory flushing, it is not even standardized. The acceptance criteria will be defined individually by each manufacturer. The standard itself highlights that if the equipment manufacturer have provided detailed flushing procedures, they should take precedence over the standard. That's right, specifically for that flushing I mentioned, called flushing for commissioning or circulatory. But if we have evidenced the high level of dirt in the oil, detected, for example, by a NOS much higher than specified, or if we have to do a more thorough filtering, for example, for the control system or for a critical process machine, how can we correct purity indicators, or provide the most efficient guaranteed flushing of all? For these cases, we have the so-called high-speed flushing. This one too, standardized, which defines objective and detailed parameters for its execution. Let's understand a little more about him. To begin with, let's understand the term high-speed. This concept of high-speed oil circulation during flushing is the main difference of this flushing. In this case, generally with the use of external pumps, we circulate the oil at 3 to 4 times the normal speed. Typical circulation of the equipment, according to the standard. To satisfy this condition, it is necessary that the flushing process reach a flow velocity above 4,000 Reynolds. High velocity flow is proven to provide the best daily cleaning and surfaces of the turbine lubrication system. In this case, requiring specific procedures such as heating of oil, installation of 80 and 100 mesh screen, bypass bearings, installation of auxiliary filters, and eventually the fine-tuned beating of all the piping, and many other technical details specific to each area of the system. As the focus of this video here is not to detail the process itself in all its details. Although we can do that there and then just contact us. I won't go into much more detail so as not to extend the video beyond what is needed. Focusing here and introducing the general concept about flushing in turbomachinery, as a way of illustrating the concept of this high-speed flow mentioned. Let's understand a basic concept of fluid mechanics. Inside a typical tube, the fluid flow is basically in the center of this tube, on the peripheries, or in regions close to the tube walls. The speed tends to 0. Below 2000 Reynolds. Well, then let's understand a little better. How does this work here in practice? As I said here, it was me, the inventor, and the one here dedicated himself to studying this was Osborne Reynolds. The concept of the number of large numbers was therefore developed there in 1883. So basically a test bench had to have a colorant, and then he introduced it into a tube to do the regime, as we will see in detail, okay? So there it is again. He doing this experiment basically about this here until here. The die, and it was introduced into the middle of a flow regime. And then he walked here, and then he observed and classified the regimes. So laminar, transactional, and turbulent when there is a lot of agitation there, okay? So, basically it works like this here we would have in this situation. A laminar regime, and it begins to have a transactional. That it starts to oscillate a little, and here it is already the turbulent regime. So notice that here we have almost no drag whatsoever in any of these regimes. So the Reynolds number in pipes below 2000, laminar flow, transition flow, it goes from 2000 to 2400 and above 2400. We have the so-called regime. The flow is turbulent. That's for Reynolds concept. But for high velocity flow standard ASTM D6439, the requirement for doing so-called high-speed flushing requires travel speed above 4000 Reynolds, as we already said a little bit here. So we have another experiment. Also to elucidate all this, to illustrate it better. So here we have inside a tube. He's circling here for a bomb that's behind and in here. It has glitter to simulate deposited material. And here there is a mirror so we can see exactly this material deposited here. So, here there is a low circulation speed. Laminar flow, for example, is typical of standard turbine system pumps. So we will always have this system rotating with this flow. Then it will increase a little bit. It will reach the transition zone. Increasing the Reynolds number, we begin to see a already dragging material. However, it still remains in suspension. Here is the deposit of this simulation, the accumulation of material. Organic, lees, varnish, sludge and everything else. Despite collecting everything that ends up in the turbine lubrication system. And then finally it increases this flow. At ratings above 4,000 Reynolds, it already starts to drag, so there. That material is deposited and it reaches 15,000, 20,000. Where finally he in fact agitates and by the turbulent regime, it ends up releasing and throwing all this deposited material into the oil. And then yes, then we will filter. The objective is this, because, at the same time, we are filtering this oil. So we have separate pumps there, working, operating. Here is another video to go into a little more detail. For us to understand a CFD vision, right? How does it work? Then in the laminar regime, the fluid stays right in the center. The hustle and bustle there begins to pass through the transactional zone, an intermediate region, until finally it begins in the turbulent regime. So we see that we will in fact have greater mobility of all these compounds that are in suspension, that are deposited there. How? With difficulty in being removed, and then the laminar regime. Speed as a function of time and the turbulence that we create, right? So the higher our speed, he will show that the greatest amplitude will be this agitation. This amount of immobility, of deposit. Here is simulating and showing. Here we will highlight a particle in suspension. So notice that in the center of the tube, in the case of laminar regime, we have high speed and more on the periphery that it will tend. At zero speed, so this material will not even be moved. In the turbulent regime, however, no. We have all the points there, the entire periphery. The radius of action of the flow is much greater. And then there are other factors that are not relevant to those who have a lot of details. And that's because this need for high travel speed. On the other hand, high-speed throw is considered the most effective. Typically standard pumping system of turbo machines. They operate with displacement and flow below 2,000 Reynolds. That's to preserve the machine's devices. Mainly the bearings which are more sensitive, for example. Since a high-speed displacement, it has to increase the oil pressure inside this lubrication system, which can represent problems for the operation and increase the associated risks. So, it is exactly in this scenario that turbo machines in general operate in the low oil flow speed regime, precisely, where accumulations of particulate deposits occur. Sludge, varnish, sludge, wear and tear from all types of contamination. Deposited in the pipes, parts and pieces of the lubrication system. Hence, then, the need for this high displacement speed provided by the high-speed flow, precisely to provide the turbulent regime, thus achieving, with greater intensity of agitation, the ends of pipes and lubrication systems, thus dragging all the deposited material into the oil, which in turn is simultaneously being filtered. It is worth noting that the standard on flushing does not define the necessary pressure. Nor could I. After all, the pressure will be corresponding. The energy required for high-speed flow to occur. The entire flushing process can be quite time-consuming, which can last for days or even weeks of high-speed circulation and filtration. It will depend on the level of dirt in the oil. To give you an idea, another well-known standard on this subject is ISO 23309 says that the high-speed flow process time, it must be at least 20 times the internal volume of the tube, divided by the pump flow rate. Taking a tube as an example, for example, 3 inches by 100 meters long, the passage time can be 20 minutes only in that session, being that to achieve, in the turbulent regime, a flow rate of 460 liters per minute will be required. Finally, and to conclude the main topic of today's video, it is also worth highlighting another type of flushing with cleaning additives, better known, such as chemical cleaning plastic or also flushing varnish remover. In that case, solubilizers are used together in high-speed flushing, surface activators and other products for sounding varnish precursors. That's it, we can capture them, regardless. Whatever type of flushing is to be performed, it is obvious that always must be carried out by qualified and experienced professionals. The standard itself even calls this the case. If you are in need of support or a proposal for the execution of high-speed flushing services, circulatory or chemical nail polish remover. Know that we have a robust structure to meet your scope, performing services and obtaining 100% results, in accordance with the aforementioned standards. As you know, TURBIVAP works together with Relodyne Lubritech, our business partner and expert in this subject, having performed more than 1,300 flushings in the last 10 years in Brazil alone. For the largest companies in the sector, such as, for example, carrying out the full commissioning of the P51 platform, all piping above and below the hull, including chemical pickling and high-speed flushing, we are available to meet with your team and explain everything. Our working method, study and understand your system, your flowchart, present our calculation report, eventually going into the field to deliver our concrete solution, including for smaller generation units as well. It's not just for big clients, no. Be sure to check it out. It will be a pleasure to be there in person at your company and your next flushing. The links will be here in the video description and on the card too. Any questions you have and need support, a consultancy and even free training, we come to you. Today's video ends here. Thank you for your attention and company and see you in the next video. I went.